I'm going to show you how to actually build a model in BESMod and simulate it. And I'm going to give 3 examples to show different use cases or applications of BESMod. And yeah, then you have a little bit more hands-on examples. To simulate in BESMod, you have to follow these steps. You have to redeclare subsystems. So the full energy system looks like this. You have to replace all these gray icons. So generation, distribution, transfer, control. So in total, I don't know, 5, 6, 10, 14, 15 subsystems you have to redeclare. But you can use existing ones if you, for example, just want to simulate hydraulic and electrical and don't want to simulate ventilation, you can just disable it. You have to select component data and fine-tune if you want some bottom-up parameters. So for example, room set temperature. Then you have to choose a weather file and override if you need parameters which you want to study. So for example, I'm doing design optimization. So I maybe want to analyze the size of the heat pump, and then I can kind of select a record here which contains this parameter to study. And then you can click on simulate and it will hopefully work. And I will now with you together compose one system which consists of an hydraulic system with a monovalent gas boiler, 2 storages, so for space heating and domestic hot water, and radiators to transfer the heat to the building. And we have an electrical system with PV and a direct grid connection where we can consume the electricity we generate. But as this household owner has gas plus PV, he did not thought about investing into a battery, let's say. And yeah, this system I will now build up with you in BESMod. And to start, you always have to extend the following base module, and it's called partial building energy system. We could also consider moving this at a more prestigious place, maybe not in base classes, but all final examples always extend from this partial building energy system. And if you recall the icons you saw previously, you will see that basically all icons are just these containers. And now what you can do, I'm going to start a new package because I would say, okay, I want to add maybe more modules or models afterwards. And I'll just call that example tutorial and create a new package, which I can later on save in another location. Then I can go on right click, new, extend from, and I can insert the new model into this examples tutorial and say, okay, this model is just called building energy system. We could also call it building energy system gas, PV, yeah, something like that. Okay, and now comes the part of redeclaring all modules. And this is basically yeah, the main modeling part. So you don't have to connect anything. You don't have to go into the text of Modelica. Everything is graphical, so you don't have to change anything. But like redeclaring and selecting the different options you have will take some time. And also, especially at the start, you may have questions on certain models, and then you can just ask them or select them and play around with it. To redeclare everything, I would advise to go to right-click parameters, and now you see all the options you have in for the parameterization. By default, the medium in the hydraulic system is water, in the thermal zone is air, and in the domestic hot water space it's also water, so you don't have to change anything here. And then you have these different blocks. Typically, to see if you have to still redeclare something, Dymola offers these nice little, I would say, holes or gray boxes, which show you that you still have to replace something. And if we now start with system parameters, I will now kind of redeclare it and explain what a system parameter is. So we can go on edit to see what is in there. In the system parameters, you have the nominal heat flow rate of the building. You have the number of thermal zones you want to simulate. You have the nominal outdoor air temperature, nominal room set temperature, then nominal heat transfer temperatures. So, for example, this is the temperature at which the radiators are designed. So, for example, 55 degrees, and also further assumptions which you don't have to change, like domestic hot water temperature, cold water temperature, ambient temperatures of the systems. So it's typically in the basement. And which weather file you want to simulate, and if you want to disable certain systems. So for example, you can say, okay, I don't want to simulate the ventilation system. And then you can say false, and it isn't simulated. Now I will select the example system parameters. The example system parameters are written for the case of a building in Potsdam. So you have weather data from Potsdam. Potsdam has -12 degrees nominal outdoor air temperature. We use it for the thermal zone model of the XLIP. So we have one zone which has a heat load of roughly 10 kilowatts, and we size the radiators to be to require 55 degrees supply temperature at -12 outdoor air temperature. And we for now want to simulate all the systems. Then I'm not going to do any parameter study yet. So I'm just selecting, I don't want to study anything. So it's just an empty record. Nothing is in here. Now I will select the building. As mentioned, we have 3 cases. So high order model, best test case 600 from buildings library, and teaser. I will select the teaser model. And now, as a rule of thumb, if you change or redeclare models in Dymola, as soon as you see this little table here, you kind of always have to click on it to check if there's anything further down the road to change. So if we want to now parameterize the building, we see, okay, to simulate a building, we have to select information about the building. And if we only have one zone, which is the case in this example, we can just redeclare this one zone parameter. If we would have an area of zones, we would have to change this area here, but this is not as nicely implemented in Dymola. So I will just redeclare this one. This case 1 was from a study at the BAUSIM conference, and this is the typical system building envelope from Germany based on Fehring's Coolhead framework. And we are now going to simulate the retrofit case just as an example. And then you can specify, for example, additional ventilation rate. You can, for outputs, disable that all the energy balances are calculated. I would just leave it on. The bandwidth for thermal comfort, this is according to 15251 European norm. And as you can see here, all the building geometry is already defined by the zone parameter, so we don't have to change anything here. Clicking OK, we can go to user profiles. As we model the model with teaser, we also have to use the teaser profiles, which are relative inputs. Again, we have to go into edit and see, okay, the file name is already selected to be the default one in teaser, but you could change it here. And you can also amplify or reduce internal gains by this gain value. You just keep everything standard. Then for the domestic hot water system, we currently have only one implementation. So you select the one, and then you go onto parameterization. Again, you have options here. You can say, okay, domestic hot water profile. I want to simulate maybe profile M, which is according to European norm as well. You could use domestic hot water calc, then you have to specify table and so forth, but we don't do that here. And now comes first component, like physical component, which is pump data. So what is in pump data? Pump data contains information about the mover of the system. So we specify a relative pressure curve. It's implemented the way that you will always achieve the nominal mass flow rates you want if you operate at nominal conditions. Aside from that, you will have part load behavior. Then you have different options here, like add power to medium, use the input filter, and so forth. So typical values you would have to change for a mover. And to not have all these parameters in this view, I can just say, okay, I want to simulate the default mover. And the default mover doesn't add power to medium. I don't use an input filter. And it's just basically the standard example. But now if I want to simulate, for example, a mover with input filter, you could just extend the record and say, okay, I have a mover with an input filter. And you will just have to select this instead of changing the parameters at all places, in all places. So this is basically a nice feature of using records for parameterization. And then we have a modeling option for this domestic hot water system, which is not very well documented. Shame on me. If you find that you don't understand something, just raise an issue and ask. I will be happy to update the documentation. Yeah, otherwise, yeah, I will add certain information afterwards as well. So here you have 3 different options to basically calculate how much water is going to be extracted from the domestic hot water tank. And I will just say, okay, dynamic way to calculate this. So if we have a higher temperature, we can basically mix cold and hot water and yeah, limit the amount of mass flow we're going to extract. And then we have more bottom-up parameters here. This part, these all have a default value. If there's a default value, you can, for now, use it and assume that my knowledge about hydraulic systems is good enough to give you a typical case. So, for example, the nominal mass flow rates, the nominal heat flow rates, and so forth are all according to norm. Then you have to size the domestic hot water storages. This critical periods is all based on norm. So if there's a default value, you can challenge it and say, okay, I want to optimize this default value, definitely. But to get started, you can just leave these bottom-up parameters and trust that it's correct. And then I have to kind of go into the real component physics. For the electrical system, we have 2 options. First, build your custom electrical system. You have these options for all hydraulic and ventilation systems as well. And this basically enables you to just fine-tune the generation, the distribution, the transfer system, and so forth. But we also have predefined systems. So for example, here we just say, okay, direct grid connection. We don't have any PV system, no generation, no transfer whatsoever. And so if you don't want to simulate basically the electrical system, you can select this one. And now we want to do a PV system. So we choose build your own. Then we go again into this table view because there's more to redeclare. Then we have to select generation, distribution, transfer, and control. For generation, we can specify we don't want to generate electricity, but we want to simulate the PV system, so we choose PV. Again, we have to go deeper down the rabbit hole to find even more options. So you see the parameterization in Dymola is really handy to work with BESMod. This one, actually, I don't know which to select here. So Laura Meyer implemented this model. She would know. So I'm just selecting the first option here. We could go even further. I've never changed it, and she didn't either. So I'm going to trust that this validated model of PV is good enough. And I'm just selecting maybe this Chico as PV system. Okay. And then we have to, these 4 parameters are still blank. And we can say, okay, we know that we have a weather data, and all this information, longitude, latitude, altitude, is contained in this weather data. So basically, this could be an improvement for the PV model in the XLib to not specify this as a parameter, but instead use the information from the bus connector. I will raise this issue after this tutorial, but it's nothing you can kind of, it's not too complicated to change. And then we have as well bottom-up parameters. So for example, how many modules are going to be used. And you see this is automatically calculated based on the roof area available divided by the area of one module. So if I have 50 square meters and one module has 2 square meters of area, you can put in 25 modules. And we have another design factor, which says it's kind of over-undersizing factor relative to the roof area. So we can say, okay, we want to have 50, or in this case, it's 80% of the roof area is filled with PV. And we can also say, okay, this roof area is kind of a top-down parameter. If we assume that we have a building which is tilted to the south, we can only basically use half of the roof area because the other one is tilted to north. So we could change this and divide it by half or something, but we can also just say, okay, we only use 40%. So this is kind of an example on how the parameterization is simplified a little bit for you, but you still have to kind of think about what you're going to model. Then for the distribution, we said we want to have direct grid connection with own consumption. So a pretty standard option. We don't have any further parameters here. Then for the transfer system, there is no transfer system. We don't simulate direct electric heating. Could be a really good study after this winter. I guess a lot of persons bought one, but you can also can't change anything here because there's no transfer. And as we can't control a PV system, we also don't have any control model yet. Stay tuned for the rest of the workshop. And we are finished with the electrical system. Then for the hydraulical system, again, we have to build it up on our own because there are no predefined options yet. We can now change, okay, we wanted to simulate a gas boiler. We also have just a heating rod, bivalent, a mono-energetic heat pump, no heat generation, and then solar thermal assisted heat pumps based one time on the XLib solar thermal model and one time on the building solar thermal model. So different options. You simulate the gas boiler. Again, go further down the road and say, okay, what do we have to define? Well, we have to select the component data in here. We have to specify, okay, which boiler do you want to simulate? As you remember, it was a retrofit building, so it has definitely below 10 kilowatts of power, and we don't have smaller boiler option. So we use this record for the boiler. This efficiency table you can change, won't do it now. Then we select data for the temperature sensors and the pumps. So pumps, you already know from the domestic hot water system. The temperature sensor is kind of the same. So you kind of specify, okay, do I have heat losses from the ambient to the ambient? What is the time constant of the sensor and so forth? And then we have a missing bottom-up parameter on the top part here. All the other things are parameterized. So for example, the nominal pressure loss is given by the boiler model. The mass flow rate is automatically calculated based on the heat demand of the system divided by the nominal temperature difference of the system and heat capacity. But the nominal temperature difference of the boiler is not given. This is basically because I'm not an expert on boilers. If you simulate the heat pump model, there is a recommendation in the European norm on which temperature difference to use at which temperature demand level. So this is automatically calculated for you. I would just say, okay, it's 10 kelvins. I don't know if it's a good assumption, I guess so. So anybody disagrees, just state it. And now an important part is these bottom-up parameters are always arrays because we have multiple circuits we can supply. So instead of putting just the 10 here, you will get an error that the value expression is illegal. This is because BT transfer nominal is an array and you just tried to put in a scalar value. So you have to specify it as an array, or you can put it in here on the table view. Okay. For the control part, we want to simulate all this is for heat pumps. Want to do a PI control of the gas boiler, which is given. Again, we can redeclare options. I will do this a little bit quicker because basically, if you have further questions on this specific control, you can ask me or look at the code on how it's implemented. Basically, we are going to simulate a smart thermostat with default control values and a PI controller with the default settings. So everything default. You can, for example, change the heating curve in this simulation part here, but for now, let's keep it simple. For the distribution, we said we want to have 2 storages. I'm going to go with the detailed storage models from the AkeSlip, one with direct loading of space heating, and the domestic hot water always is indirect loading. And again, we have to kind of make parameter changes. So we can say, okay, according to 15450, how do we design the domestic hot water storage? I would go for part storage, which is often used. You can read more in the European norm on what this means, but for now you can just use often the default values. We don't want to simulate a heating rod in the storage. We use default record data for these components, just always the default option and default heating rod and so forth. And we don't want to use this is a component choice. There's an option to simulate a heating rod, which comes just after the thermal energy storage, but we want to disable it now. So you also see that these options are now gray because we can't change it, because we don't simulate it. Maybe one note on these records. It's now called default detailed storage. If you go and look at the parameterization, again, you have, let's say, first attempts to simplify the parameterization. So you have storage geometry, which is a storage height to diameter ratio. You have a parameter also according to norm on how to size the thermal energy storage based on the heat flow rate required. Then you have for the installation, for example, information on how much kilowatt hours per day are going to be lost. And now this is all for default storage, I guess a relatively new storage. But what we could do is kind of implement 10 different records, one for a new storage, one for an old storage, and then the users don't have only one option to select from, but kind of 10 different, and can say, okay, I'm going to use an energy efficient storage. So even though all these records are currently just one option, you can either manipulate the values directly in here, or you can implement fitting options which are relevant to your research as well. And last, the transfer system. I'm going to go with the pressure-based transfer system, which contains radiators. Again, if you don't know, based on this documentation, what is meant by this model, you can also just look into the modules available in BESMod and kind of look in the documentation and model phase, what is being modeled. And again, here we have to make some component data choices. So going to use steel radiators. Then I'm going to use default mover again and default parameters for the radiator. All is based on norms and standards. So you can, again, change these parameters, but you at first sight don't have to do this. I'm going to disable the pressure relief valve because we're not going to use it. We have a thermal energy storage. We don't need it. And also up here is an example for, on how a bottom-up parameter works. So the nominal mass flow rate is automatically calculated based on the heat flow rate required and the temperature difference. And then the temperature difference is this fairly long if clause. And what we basically see here is as soon as we have 65 degrees Celsius or higher temperatures, we use 15 Kelvin temperature difference. If we are higher than 45 degrees Celsius, we use 10 and else 7. And this is basically typical values for radiators, and 7 is for underflow heating. So based on the temperature level demand you have, you can kind of trust that these nominal values are according to standard. You can change it if you want, but you kind of can go with the default for a start. Okay, and to limit the size here, we're going to say we don't simulate any ventilation, and we don't have any supervisory control, which complicates things further. There are examples for ventilation and for control, but we are not going to do this now. Now you see that everything has changed. Everything now is selected. I will quickly go on save, because even though Dymola is pretty robust, sometimes it fails. So by default, we are in the working directory of BESMod. I'm going to click save. And now hopefully simulation works. I just clicked on the slides, so I haven't checked if it works now, but I guess it's a good, maybe if it does not work directly, because then you can see also how to handle errors. Okay, it works on first try. Then you have to come with error messages afterwards to me, and we can click on simulate. Before I'm going to click, I will quickly change the simulation time. It's 1 second. It's not that interesting. I will simulate the first month, so the month January, and select roughly 10 minutes step size. Click on simulate, and now we see how the simulation evolves. Maybe also if you have in the meantime any questions, just like write them in the chat and I can read them and answer them. And now you see here down here it's simulating, and you have all these different systems, and you could go into the subsystems. But for a first analysis, you should always look for the outputs of the system. So this outputs bus, I mentioned that the outputs contain all relevant information. So if we look at the building, we see temperature of the zone. Perfect. You can directly see, nice, we have a really good control behavior. First overshoot at initialization, but afterwards we have a really good control behavior. We can also see, okay, delta T discomfort of cooling. So we don't have any cooling phase because it's winter. We have at the start of the simulation a slight discomfort, but I mean it's initialization, so you should always not consider the initialization fast. And we have also information about how much, for example, we gain through internal gains. So we have the value. These are basically the load profiles of teaser. And we also have automatically calculated for you the integral value, so you know the final energy consumption. And this is also true for the components. So you, for example, in the hydraulic system, you can go to generation and look at the heat flow rate of the boiler, see the value, and see the integral. And for the component, the boiler itself, you can also see outputs like number of switches, total on time, so metrics which are typically used to analyze the system. And also in the electrical part, you can say, okay, how much electricity did we generate? Not that much. I mean, it's winter still, so did not have that much input. And also in the distribution phase, we can see, okay, what is basically the generation, how much heat we generate to the grid. And we see that it's equal to the electricity we generate with the PV, because we feed everything in. And then we have the load on the system. And we see here that it's basically I guess it's just the pump. So it's basically nothing. Just the mover is included here because the boiler is using gas and not electricity. Okay, there's a question. New base model, including all of these generators. To connect the generator partial model. So if I understand it correctly, I will quickly answer the question. The question is, to model multiple generators, you would need to add a new base model, including all of these generators, correct? Or is there some crazy new creative way to vectorize and connect the generator partial model? I hope that the following example shows on how to connect multiple systems. So in here, in this example where we have two parallel systems, you see that in the parameters of the model, we have two different circuits we want to supply. But this model contains the heat pump and the solar thermal. But the heat pump model is in here. So you kind of can just extend this model, or we extend this model, and only add the part for solar thermal to add basically another dimension. What you could also do, okay, perfect. And what you could also do still is basically drag a system in here and kind of say, if I have like 5 different circuits, you could also say, okay, I'm going to just drag these in, connect all bus connectors, and then don't limit the amount of code you have to write again. So this is also an option. Okay. If that does not make sense, okay, then it seems to be clear. Okay. And now for the simulation, we can analyze everything in detail, also like how much energy is used in the domestic hot water system. We can also go into detail into a single component. So for example, in the hydraulic system, into, I don't know, control, and then let's say into the heating curve, for example. So everything is there. So TZ changes based on outdoor air temperature. But that's not that important. If you want to analyze the system further, I would always advise, okay, to look using the show component option. Okay, what did I now model? Because now you kind of selected all these options and made a lot of assumptions. You can trust me that these assumptions are according to norm, but still you should know somehow what is happening. And I would really advise to look at the models. Okay, what is happening here? So in the transfer system, we have a pump, resistance, volume of the hydraulic network, thermostatic valve, and a radiator. So you can look at this in a graphics view and kind of understand what is happening physics-wise. So in the storage, you have a 3-way valve and 2 storages. But I'm not going to go into much detail, but I would advise to always question simulation results and always run different scenarios and boundary conditions to really understand if something is kind of real behavior or if it's just a modeling error, because that can happen as well. Okay, so this is basically how you simulate. This was the first example. We have still 20 minutes to go, and I will quickly show another important example, which is comparing 2 model approaches. So if you want to use BESMod, you can really quickly compare 2 different model approaches, because as you can just redeclare this single subsystem, it's let's say scientifically robust, because you know everything else stays the same. And we can implement this now by changing in the scenario that the house owner says, okay, I'm going to buy a heat pump, and see the effect on the system. So again, we're going to go into our model. And what we are now going to do is use inheritance. To some of you, it may be a new concept, but inheritance, if you are doing research, is a really good concept you should look at. So what we are going to do is we say we are going to extend from this model and call this building energy system with a heat pump. And what we now see, okay, we don't have any options here because we already redeclared everything. So what we have to do basically is say, okay, I'm going to remove the identifier or the modifier from this generation model. And now I have the option to select in this heat pump model the monoenergetic heat pump system. Again, we have a lot of options. I'm not going to go into too much detail. We are simulating an air source heat pump. So it's an air source, and we are going to be using a heating rod. We just use manufacturer data. So this is all in the XLib model examples. If you want to understand further about the heat pump model, we are selecting. Now that takes some time. I don't know why actually. And I hope it doesn't crash. Dymola. We're going to select a air source heat pump, which is Vitocal 350. Then just using again the default values. Again, you can change all these values. For now, we are not going to do this. And now we have, if we go on show component, still the same storages. We didn't have to change anything, but we now have a heat pump and a heating rod, which supplies the heat. Now, if we simulate, I can say it won't work because I forgot something. And this is really an important part. And this is why I actually on purpose did this error. If you select systems which are not compatible to each other, the most likely error is that you get warnings. The bus input hydraulic is missing a matching non-input in the connection set. This means that the bus signal T boiler out is missing. Why is it missing? Because we removed the boiler model. So we don't have any measurement in the system. But as we can see here, the control model assumes that we need this temperature. And this is mainly because in here, I just removed the generation system, but the control system is still the gas boiler. So if I now want to control a heat pump, obviously I always have to remove the control, and now I can select a control module which is more fitting for heat pumps. So for example, a hysteresis with the PI controller, condenser outlet. Again, I will quickly select default PI values and so forth. It's constant domestic hot water temperature, and I'm not using any supervisory control. This is a little bit faster to still be in time for questions at the end. And now hopefully I did not make any further errors, and it will simulate. So these missing inputs in bus connectors kind of always means that the control system and the physical component system is not compatible to each other. If you implement a new system, it could be due to the case that you just forgot to, let's say, give a measurement to the control system. If you now only select existing modules, you kind of have to look into the models itself, what is the model about, what it tries to simulate, and so forth. And now if we look at the simulation, the building energy system heat pump is running. Again, on the outputs, we see nice. We now have more outputs because we have a different system. We did not have to change anything, add any new outputs, but we can see the behavior of the heat pump, the integral, and also the value. What we do see here is that we have fairly high switching of the heat pump. And this is due to the case that we never looked at how large is basically the heat demand of the building. And this is why our heat pump is currently oversized, and also the boiler is oversized for our system. And I will just quickly show how to calculate the heat demand with BESMod, and then the behavior should be a little bit better. So for heat demand, we can specify the heat demand in here. So this is basically the value in the system parameters. And you can calculate this according to European norm 12,381 in the systems demand building heat demand. And here you have the model for the heat demand calculation of the reduced order model. You have to specify, okay, which model am I going to simulate? I'm selecting the retrofit case. This is everything. Everything is basically according to standard. And then you can specify in the parameters, okay, at which nominal outer air temperature do I want to calculate the heat demand? I'm saying, okay, for Potsdam, it's minus 12 degrees. Click on simulate, and then you will get the total heat demand and the heat demand for all zones as an output, and also how to kind of select or change this is written in the text here. And if we now look at this Q building flow nominal, we see that if we rescale it to annual simulation and not the initialization phase, that the heat demand of the building is basically 5,600 watts. And we can now change this here. So we can say, okay, but our heat demand is only 5,600. And now, only because we changed this value, which is basically the top-down parameter for all the other models, everything will change. So the radiators will be sized differently because we have a different heat load. The storages will be sized differently because we have a different heat load. Yeah? So everything kind of depends on the heat load of the building you're going to simulate. In our heat pump model, we have to look now at which heat pump we selected. And if we look at this data table of the manufacturer, the performance data for this Q-flow nominal is really large. So we basically at -10 degrees, and this is basically roughly the design point. This heat pump supplies 12,000 kilowatts. So this is really big, 2 times actually as big as our heat demand. And we can prevent this issue by setting in the heat pump parameters the scaling factor to 0.5. So basically, the heat pump is only half as big as according to manufacturer data. This will change in the new Vipsa version, where you don't have to specify the scaling factor manually. So this is only for now that you have to change the scaling factor. But I mean, also if you want to see how a real device, according to real manufacturer data, without any scaling factor behaves in a certain building, it's also fine to just simulate it without scaling and see, okay, how different component choices work. And now if we simulate again, I will quickly click on simulate and keep this result on top here, so we can see the difference in the parameterization. We will see that the behavior is certainly different. So if we look at the most important temperature, the thermal zone temperature, we see that also now the radiators and the heat pump are able to achieve the temperature requirement. If we compare it to this model, it certainly has little bit worse control behavior because the radiators are way smaller, but still the control behavior is plus minus 0.5 kelvins, so still pretty good. And also if we look now at, for example, the storage volume in the simulation up here, we had hydraulic, distribution, storage, storage parameters. We have roughly 250 liters of storage volume. And down here we have here a little bit less, so only 130 liters, because we roughly have half of the demand, so we don't need that much inertia. So all of this is changed according to norm. So every time you change the heat load, you will have basically different design of the energy system. And now if we look at how the heat pump behaves, we can see that without this option, we can see that the value, it's a lot more continuous. So let's compare it to the simulation before. We definitely see that the first oversized heat pump led to a lot of switching behavior. It switched nearly 180 times in the winter, and now we only have 60 switches. So reduced it by factor 3. So this kind of demonstrates on how to change the design, how it affects the system. But most importantly, you always have the important KPIs in the output bus to analyze on how the system is working. And you can kind of make studies based on that. And now if we kind of want to compare heat pump and gas boiler, we would have to kind of duplicate this one and say, okay, this is now the building energy system with gas boiler, and change this system again to a gas boiler. And now we have two models, one with the heat pump and one with the gas boiler. Quickly select the F kilowatt device, specify the heat load and the component data a little bit quicker this time. And now we can basically really easily compare these two models and see how the gas boiler and the heat pump have different effects on the system. In the last 5 minutes, so really quickly, this will be possible still, I want to show how to run a parameter study with BESMod. And I planned another thing on how to add new modules. I will just continue and annoy my office colleague a little bit further and just continue afterwards. If you have to go in 5 minutes, just go. Else, yeah, stay and listen. And so on the parameter sweep, we want to select the size of the PV system. And to do this, we kind of can use this record parameter study. If we open it, we see that it's just, now we selected the no study one. We have in here all the important information which is necessary to do a parameter study in Dymola. So we can extend from this record and say, okay, PV size study, something like that. And we want to include it in our own package. And now we can say, if you recall, we have a parameter design factor, which defaults to 80%. And this design factor was used to calculate the design size of the PV system. And we want to sweep this parameter and check how it affects our results. If we implement it like this, it sometimes does not work because we forgot an important information. We always have to evaluate like equals false to this parameters we want to change. So these values become accessible to sweeping. And this, so you don't have to basically use this record, but having worked with a few students, I found that it helps for the mind to know, okay, everything which defines my system is in this record, and everything which I want to change is in this record. So you kind of have it just separated in mind. You don't have to use it. You can also specify it anywhere else. But from my experience, it helps. And so we select our new PV size study, and we're going to simulate it with the heat pump case, because that's maybe a little bit more interesting. And to do a parameter sweep in Dymola, we first have to simulate it once. And oh wait, I forgot to actually change anything and use the design factor. So I have to go into the PV model and say, okay, this array is parameter study.factor design. Again, we have to think about that this is an array, and we have just one dimension. Now we actually using the factor to do anything. And I'm going to simulate and wait for translation. Maybe as the official time runs to an end, have you any questions at this point? So just write them in the chat if you have. Translation is high enough. Now we can go in Dymola to simulation, sweep parameters, go to the parameter study. This little field here shows that you can sweep this parameter, and this is because we set evaluate equals false. So we drag this one over here. And now we say we want to look at how much electricity we are going to feed into the grid. So see, okay, what is the generation to the grid? And we are using the integral value, and then we can say it's only last point, because then the integral at the last point is basically the energy demand. Say, okay, we want to sweep from 0 to 100% of roof area, and we do this 4 times, and then run sweep and really quickly analyze on how different PV sizes influence the amount of electricity we generate. Kind of have to wait a little bit, and yeah, while this finishes, this is, I guess, a good overview for all of you on how to use BESMod. What is the first concepts and so forth, how to use it. If you're interested in using it, yeah, just feel free to use it. Look at these workshops again, try to work it through on your own. If you find any issues, just raise them to BESMod, to the GitHub repository, and always ask there, because it's open source, so everybody can see the discussion. And you can also write me email or Slack message. And then in the next half hour, I will quickly show on how to implement a new model. And what we now see here in this nice plot view, okay, is the more PV we size, the more electricity we generate. If we don't use PV at all, we don't generate anything. So this is kind of plausibility study, so it works. And if we use our full roof area, we have somewhat 7 times e to the power of 8 joule. So not in kilowatt hours, but I guess I can, oh no, I can't change the unit here. Here I can change it. So 200 kilowatt hours in the January month of the year. So pretty good. And we can also see, if we look at the results, basically how, for example, the heat pump behavior changes a little bit. Okay, so this finishes the part on how to simulate, and I hope by showing how to compose a simulation, how to compare 2 model approaches, and how to run a parameter sweep, I teach the main important concepts of BESMod.